Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, without further ado, let's get right to the phone calls. Let's have the first listener phone call.
I'm wondering why the International Space Station is not shaped like a giant wheel as designed by Wernher von Braun. Thank you.
Well, good question. If you saw the movie 2001, it starts off with gorgeous, beautiful spinning wheels in outer space. And to answer your question, there's a dirty word, a four-letter word, C-O-S-T. Cost. It simply costs too much to create spinning wheels in outer space. Now, why bother to spin a spacecraft at all? Because you want artificial gravity. Without gravity, you are weightless, and all sorts of bad things happen to your body. You have muscle deterioration, loss of calcium and phosphorus and other minerals from your bones. In fact, your spinal cord even expands about 1.5 inches to 2 inches. You actually are taller being in outer space. So you have all these problems dealing with weightlessness, and the way to eliminate weightlessness is to get artificial gravity. That is, spin the spacecraft. We've all been at carnivals, and at carnivals, they spin you around, and you feel a force pushing you into the chair, and that's called centrifugal force. Now, we could do that with the space station, except it would cost an awful lot of money. That's why the space station looks like a bathtub. It's very inelegant. It's not streamlined. It doesn't take your breath away at all like the wheels that you see in the movie 2001. But hey, they work, and it just means that our astronauts have to do exercises in order to keep their muscle toned, in order to keep their bones from disintegrating. They have to constantly exercise in outer space. So in the future, maybe we'll have spacecraft that do spin, for example, going to Mars. The trip to Mars will take about 9 months. That's an awful long time to be under weightlessness. And so some people have said that maybe we should spin the Martian spacecraft to give them artificial gravity. Well, yeah, great idea, but it boils down to one word, cost. It costs about $10,000 to put a pound of anything in orbit. That's your weight in gold, just so you can orbit the Earth. To put a pound of anything on the moon costs on the order of $100,000. And to put anything on Mars would cost upwards of $1 million a pound. So it's very expensive to create spinning spacecrafts. We could do it. It's an engineering problem, but basically it's a political and economic problem. Basically the question is, who's going to pay for it if we have spinning spacecraft? Okay, let's move right on to the next listener phone call.
Dr. Kaku, my name is Ralph, and I'm listening from Great Falls, Montana, on station KQDI. And my question is, I know we have seasons because the Earth's axis is tilted, but what I would want to know is the reason why we're tilted is because the theory is we were hit by an object billions of years ago and threw the axis into the tilt. What the Earth be like if we were never hit by that object and we didn't have that tilt? What would our climate be like? Thank you very much.
Well, you ask an interesting question. When I teach astronomy at the university, the first day I ask the kids a simple question because I want to know how much they know. I ask them a simple question. Why is summer hot and why is winter warm? And I give them an array of possible answers. One of them is that maybe the sun is closer to the Earth during summertime, and the Earth is farther away during wintertime. The other is possibility that maybe the Earth tilts, and third, well, maybe there's another reason. And the answer I get from the kids is uniformly the same. About a third of the class swears that is due to the fact that the Earth is closer to the sun during summertime. That's why we have summer. A few holdouts, maybe like a tenth of the course, says, no, it's a tilting of the Earth. Because of that, not every place on the Earth gets equal amount of sunlight. and that causes the seasons. And about half the class don't know at all. Well, the answer, as you probably guessed, is the Earth tilts 23 degrees approximately. And that's why summertime, the northern hemisphere is tilting toward the sun, while the southern hemisphere is tilting away. That's why when it's summertime in New York, it is wintertime in Australia. So how do you explain the fact that it's the opposite season on the other side of the Earth? And the reason you can explain that is by assuming that A, the Earth is round, and that B, it tilts 23 degrees. Well, let's take a short commercial break, but after the break, we'll answer the question, what happens if there was no tilt at all? If there was a cosmic accident and we weren't hit by an asteroid 4 billion years ago, what would it be like if there was no tilt at all? Okay, well, let's move right along now. Oh, by the way, let me answer the previous caller, and then we'll take some more listener phone calls. The caller asked a question, if there was a cosmic accident and we were not hit by an asteroid about 4 billion years ago when the solar system was being created, and the Earth does not tilt with respect to the plane of the solar system, what would the weather be like? Well, there are many cosmic accidents, of the most famous being 65 million years ago, if that comet or meteor that was destined to hit Mexico missed by just a little bit, well, the dinosaurs would still be here. That asteroid hit just at the right point where it plowed into Mexico. Enough dirt and garbage was thrown into the air to darken sunlight, plunge temperatures, and wipe out the dinosaurs. It was a cosmic accident, in some sense, that humans are here today and not dinosaurs, talking about questions to scientists. Well, the other question was asked is, what happens if the Earth does not tilt at all? Well, we would still have weather, because the equatorial plane is still the closest to the sun in terms of the angle. If you're further toward the North Pole, then you get less sunlight. It wouldn't be as dramatic as we have it today with the 23-degree tilt. And that means you would have convection currents. That is, you'd have warm air from the equator of the Earth rise, go toward the north, and go to the south in a circle. So you would have a circular circulation of wind. So the weather would be rather strange. You would not have east-west weather so much, assuming that the planet didn't spin so much. Now, if the planet spins, on the other hand, then you can get east-west winds. So our Earth has the benefit of both. It tilts, so we have dramatic changes in summer, fall, winter, spring. And second of all, it spins, and when hot air rises, the Earth spins beneath the hot air, creating wind. Kids ask the question, why do winds blow? Winds blow because hot air rises, the Earth spins beneath the air, and so the air moves with respect to the surface of the Earth. So winds on a planet that does not rotate and is aligned vertically with respect to the ecliptic plane would have a very strange set of weathers. We wouldn't have east-west winds, but they would be north and south, the winds on such a hypothetical planet. And somewhere in this universe, I bet you there are planets that are vertically aligned to the solar system's plane. We have found so far 3,600 exoplanets orbiting other star systems, and I bet you when our instruments get better, we'll probably find a handful of them that are just like that spin like a top, such that they are aligned vertically with respect to the plane of the solar system. Okay, well, let's move right on to the next listener phone call.
My name is Daryl. I'm from Ohio. As I understand, there are gases in the universe, certain gases, and my question was that if you took a lighter or something and lit it in space, would it catch on fire or explode? Is there any chances of that happening?
Well, you ask an interesting question that a lot of people ask, and that is, can you light a match in outer space? Well, the answer is no. In order to get a match going, you need at least two things. First of all is you need fuel. Second of all, you need oxygen. Oxygen is the oxidizer, and the combination of the two gives you the spark that sets things on fire. Now, you've probably seen astronauts on the space station. They can light a match. They can light a lighter in the space station. It's not recommended, of course. And why is that? Because there's oxygen inside the spaceship. As long as there's oxygen there, you can light a match and have combustion. However, you cannot do that in outer space. You cannot do that underneath the oceans. For example, some scientists have speculated that if they are aliens in outer space, more than likely they may be aquatic, because we see lots of evidence of oceans in outer space, like in the moons of Europa and Enceladus, the moons of Saturn and Jupiter. So if there are aquatic species, will they become advanced, technologically advanced? Well, maybe, but there's a problem, and that is you cannot light a match underwater. You need an oxidizer. And since there's very little oxygen in the oceans and it's cold, you cannot light a match under the oceans. You cannot light a match in outer space. Okay, well, let's move right along to the next listener phone call.
My name is Edward from College Station in Texas. My question is, why is it we can see out there deep in the universe with Hubble, but we couldn't use it to see Pluto?
Well, you ask a very interesting question. First of all, when we look at radiation from the Big Bang, the radiation from the Big Bang, of course, is spread out. However, Pluto is a very tiny object. Its angular distribution with regards to the Hubble Space Telescope is very, very tiny in terms of seconds of arc. So we do have pictures of Pluto from the Hubble. We do have pictures. I've seen them. They're not very impressive. Of course, since then, we have sent the New Horizons spacecraft to Pluto and have gorgeous pictures of the flyby that took place. In fact, there's even one side of Pluto with a gigantic heart-shaped plains on the surface of Pluto. We also know that Pluto has moons, more moons than we previously thought. So Pluto is much more complex than we originally suspected. And again, the Hubble Space Telescope does give us fuzzy pictures of Pluto. So it is very tiny. It's a very tiny object out there. And even the Hubble Space Telescope strains to pick up that radiation. Also, the radiation from the Big Bang, some of it was collected not by the Hubble, but by the COBE satellite and the WMAP satellite. And they scanned the heavens for that radiation. You've probably seen those pictures of the explosion itself. Go to nasa.gov, type in COBE, C-O-B-E, or WMAP, W-M-A-P, or microwave background radiation. Google that, and boom, you can actually see what the fireball looked like. Yes, it was a fireball. You can see the ripples of energy. And that is a baby picture of the infant universe about 300,000 years after the instant of creation itself. So, as magnificent as the Hubble Space Telescope is, there are limits. For example, if the Hubble Space Telescope is pointed at Neptune, again, you see a fuzzy ball. You can actually see dark spots on Neptune and things like that, but not much more. There are limits to the Hubble Space Telescope. Okay, well, let's take another short commercial break, and once again, you are listening to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. That's right. Give us a call. Leave your name, call letters of the radio station you're listening to, and the city you're calling from, and perhaps you can get on Science Fantastic. Also, if you get National Geographic Channel, tune in to Year Million. I'm featured in all 6 episodes of Year Million, talking about the future, not just the future 5 years from now, the future 100, 1,000, the future 1,000,000 years ahead. What is it like for medicine, for longevity, for health, for space travel, for our mind, for artificial intelligence? All of that discussed in the latest Nat Geo TV special called Year Million. Okay, well, let's move right on now to the next listener phone call.
Hello, Dr. Kaku. I'm familiar with Einstein's idea of gravity. You know, you've talked about this trampoline, and dropping a bowling ball on the trampoline, and that's kind of how the gravity field operates with other objects in the universe. My question is this theory of gravity, this compatible with the notion of gravitons. I'm not completely sure about that, so I was hoping you could shed some light on that. If you have really short time for another question, if you could quickly perhaps just tell us, how did we discover the atom? We look around, was it with microscopes? How did we find out what the smallest blocks of the universe actually, the nature of that object? So thanks for taking my call.
Okay, well, you ask a very interesting question. If you are a Star Trek fan, you know that they have graviton beams. And people ask the question, well, what is that? What's the difference between gravity, Einstein's theory of curved spaces, and gravitons? Well, a graviton is a particle of gravity, like the photon. What is a photon? A photon is a particle of light. Now, light, of course, is a wave, and associated with that wave is a particle, and the wave of light is called the photon. Now think of gravity. Think of gravity as being a bed sheet or a trampoline net, and there are ripples, tiny little ripples which vibrate on the surface of that trampoline net, and those are the gravitons. So gravitons, like photons, are small vibrations on the larger sheet that we're talking about in the case of gravity, or vibrations in light. And so that's the relationship between photons and light, gravitons and gravity. So briefly, gravity, of course, is what holds you on the floor. Gravity is what warps space and time. But ripples, small ripples on the surface of space-time, are what we call gravitons. Now, have we ever seen a graviton? Have we ever measured one? And the answer is no. Absolutely not. However, we physicists firmly believe it because eventually you must quantize Einstein's theory of gravity. You see, we have two different formalisms. One is the formalism of Einstein, which is based on smooth surfaces, which can ripple and warp. That's why we have black holes. That's why we have all the things you see in science fiction movies. That's Einstein's theory of warped space-time. But the quantum theory deals with vibrations. It deals with particles that oscillate. And how do you marry the two together? Well, at the present time, it's very difficult. It's one of the outstanding problems in all of physics. But the way we do it is we take Einstein's theory, we put ripples on Einstein's theory, and then we quantize each of the ripple to become a particle, which is called the graviton. Also, who discovered the atom and who took a picture of it? Well, of course, the concept of the atom goes back to the Greeks 2,000 years ago. Atom means cannot cut. Tum means cut. A means cannot. So the word atom means cannot cut. But now, of course, we can blast atoms to pieces. And how did we do that? Well, let's take a short commercial break. And after the break, we're going to talk about how we can see the atom. How do we do that? Well, believe it or not, the first person to actually give us concrete evidence of atoms was Albert Einstein. When he was unemployed, he was working as a clerk in the patent office. He said that if atoms exist, they must vibrate and bump up against particles of dust, small little particles that we see, and therefore under a microscope, we should see tiny little dust particles move. Well, sure enough, you can do that. It's called Brownian motion. When you get a microscope and look at a very, very small object, you can see little tiny vibrations there because atoms buffet themselves and hit small particles of dust. And from that, Einstein got one of the first indicators of the size of an atom. Now we can actually photograph individual atoms. Believe it or not, it was once thought to be impossible because the wavelength of light is larger than an atom. Therefore, a light can only see objects down to the wavelength of light. Therefore, you can see big objects like elephants, horses, and trees. But when you get smaller and smaller and smaller, eventually you hit the wavelength of light and everything gets fuzzy, and you cannot see things smaller than the wavelength of light. But it turns out you can, using what are called phase microscopes. What you do is you get a needle, a very tiny needle with an electric charge, and you run that needle over a surface. And then you move that needle very slightly and run it over again and again and again. It's just like a record player. That's, of course, how we etch records, by having a tiny groove go one by one, creating lines on a piece of vinyl. You can do almost the same thing with atoms, and sure enough, when you do that, when this needle bumps over an atom, it registers a bump. And you can actually see this on Google. If you Google it, you can actually see pictures of atoms arranged in a crystal. We once thought that was impossible. But hey, we do it now. We can actually photograph individual atoms by looking at the distortions they make on a needle, very tiny needle, as the needle sweeps across a surface. Absolutely amazing. Okay, well, let's move right on to the next listener phone call.
Dr. Kaku, I'm sure you know about the well-known atomic Doomsday Clock. If there were an environmental Doomsday Clock, what time, in your opinion, would that clock be set at if we continue on our present course of interaction with the environment? Thank you.
Well, you ask an embarrassing question because, yes, there are scientists who say that we're at 11 o'clock, we're 1 minute to midnight, and so on and so forth. Well, that makes great copy for the newspapers, but for a scientist, it's kind of frustrating because there's so many different parameters involved that it's really impossible to say things other than that we are very close, that things look very bad for the next few decades. First of all, we are not at the point of no return. When we look at nuclear proliferation, we look at the greenhouse effect, we looked at biogerms. These are three technologies that, in principle, can destroy humanity on the planet Earth. A fourth one might be the loss of biodiversity. That is the fact that we humans are destroying other life forms on the planet Earth. But when you boil it down, the press wants to know, is it going to happen next year? Is it going to happen in 5 years, 10 years? Give us a date. And you can't, because anytime you give a date, the date is obviously going to be wrong. However, we can say some general things, and that is by mid-century, some cities could be underwater. At the rate at which the Earth is heating up, the glaciers are melting, and sea levels are rising, it means that nor'easters or storms can throw huge amounts of water right over the barricades, right over the dikes and levees, into a city like New Orleans, like Boston, New York, LA, San Francisco, and overwhelm the system. And so these are things that we have to worry about in the coming years to coming decades. With the environmental clock, some people put it at 1 minute to midnight. Some people put it at 11 o'clock. I mean, what do these things mean anyway? I think you have to break it down concretely. First of all, nuclear proliferation and nuclear war. Yes, that's something that we have to worry about. The hotspots of the world are the Korean Peninsula, as North Korea develops more nuclear weapons and ICBM capabilities. That could come to fruition in the next few years, by 2020. By 2020 at the earliest, some experts in the United States predict that North Korea will have their first ICBM capable of putting an atomic bomb on Los Angeles. At that point, the President of the United States is going to have to make a lot of military decisions, not to mention the perpetual problem between India and Pakistan. They have fought several hot wars with each other. They're both nuclear armed, and that gives pause for thought. And then we have the Iranian situation. The Iranian treaty that we signed with them, for good or bad, has a flaw. Even its supporters say that there is a flaw, and that is after the treaty expires and Iran is no longer bound by the threat of sanctions, they could go on to produce an atomic bomb. So in other words, in some sense, we are allowing them to create the infrastructure, to create the laboratories, short of a bomb because of the treaty. But after the treaty is over, they are one screw turn away from assembling a nuclear weapon. So for all these reasons, that's a problem for the Doomsday Clock. Then, of course, we have biogerms. Already we can begin to weaponize viruses. For example, if you take HIV and then weaponize it by making it airborne, then if somebody coughs, they can inhale the HIV. Well, thank goodness right now HIV is not airborne. But hey, in the era of genetic engineering, it could be possible that somebody could alter the genes so that it does become airborne, and then we are in deep doo-doo if that happens. And then, of course, we have global warming. Global warming is dangerous on a scale of decades, so don't think that tomorrow, all of a sudden, the Earth is going to be unlivable. No, it'll take years. And in those years, hopefully, politicians will rise up to the fact that, yeah, maybe we should create a world based on hydrogen, a world based on fusion, a world based on non-polluting technologies. Why not? Well, we'll have to, of course, wait and see whether the politicians have enough wisdom to see that, yes, there are some long-term threats. But exactly what time is it? It depends. Okay, let's move right along to the next listener phone call.
Hello, Dr. Kaku. This is Richard from Dallas. I was wondering, sir, if you think that cold fusion is even feasible. Thank you.
Well, ever since humans began to speculate about energy and things like that, people have proposed free energy. Energy for free. Wouldn't that be great? Put the oil companies out of business and all that. Well, there are problems. Some people think the closest we can get to free energy is cold fusion. So let me explain. Several years ago, two chemists revealed the fact that if you put palladium rods into water, the palladium rods will eventually start to release energy. In fact, energy from fusion. They claim that the palladium has magical properties and it brings atoms of hydrogen closer together. As a consequence, they're so close that you can fuse them to create helium. And that is the secret of the stars. That's why the sun shines. The sun shines because it compresses hydrogen to millions of degrees so that the hydrogen nuclei plows into other hydrogen nuclei, releasing the energy of the hydrogen bomb. That's the secret of the stars. That's why the sun shines. That's why the stars twinkle. And that's why we are here today. Now, the question is it possible that one day this kind of technology can give us free energy in the form of cold fusion? Why do we have to heat up the hydrogen? Well, it's very difficult to heat up hydrogen. We have to heat it up to millions of degrees so that protons, which don't like each other, are forced to combine to create helium and release vast amounts of energy. Cold fusion was the hope that you could do it in a bottle. Forget the sun. Forget millions of degrees. No, room temperature water could create energy. Well, these two chemists, Fleischmann and Pons, claimed to have gotten energy from almost nothing. Created a big sensation, but then it was not reproducible. And that's the key. Who knows whether it's really correct or not? I would say 99% of most physicists think it's nonsense and violates the laws of quantum mechanics. However, there's a holdout, and these holdouts think that, well, maybe one day it'll create an energy revolution. But the question is it reproducible? To be considered science, you have to have things that are testable, that are reproducible in the laboratory, or else it's a fluke, or else it's fake, or else it's another effect taking place. So far, it's not reproducible. That is, people in one country say, we've done it, fusion in a bottle. But other people on the other side of the earth, when they do the exact same experiment, get nothing. In fact, Toyota, they said, put down over $1 million to try to perfect cold fusion because, well, who knows? $1 million is not much if you're the world's largest automobile maker, and maybe it works. However, what happens when you build a Toyota? You turn the switch and it doesn't work. It's not reproducible. It is useless at that point.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific theories which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, let's jump right in and take the next listener phone call.
My name is Quincy. Basically, as human beings, how do you think it would be possible for us to achieve immortality? And when I say that, I mean that in the sense of not growing old, being able to keep our physical bodies and live forever without any degeneration. Thank you. Bye-bye.
Well, it would take a whole book to answer that question, so let me try to break it down into pieces. First of all, there are several ways of increasing the lifespan of animals. The most reliable is called caloric restriction. If you restrict their diet by 30%, they live 30% longer. This is the only verifiable testable, reproducible method ever to be done on animals which succeeds every time. You can analyze yeast cells. You can analyze insects, bugs, spiders, mice, rats, rabbits, dogs, cats, even primates now, all the way up the scale. Yes, all of them can experience life extension by eating less. There's only one animal that has not been tested, a very famous animal. It is you and me. Homo sapiens have not been tested while we do this in the laboratory with primates, monkeys, all the way down, going all the way down to yeast cells. Why does it work? We're not sure. Some people say that in the forest, animals have a choice. They can either gorge themselves on food in times of plenty and then get pregnant and have kids. That takes up a lot of energy, having kids. Or they could simply hunker down, eat nothing, and live longer and hope to ride out the period of famine and chaos. And so that's what some people think, that if you starve animals, they think that, well, we're entering a period of famine. No children are coming anytime soon, so I'll go into a semi-state of hibernation. Now, should you do that? I should warn you. People who take this diet, 30% less calories, they get irritated, they lose a lot of weight, they lose all interest in sex, they get very lethargic as a consequence. But hey, it works. What can I say? There are other methods, the most promising being gene therapy and isolating age genes. If you take the genes of old people and the genes of young people and then compare them, you see that aging is concentrated. Aging is not uniform for old people and young people. And where does aging take place? Well, think of a car. Where does aging take place in a car? Well, the engine. That's where you have moving parts, and that's where you have oxidation and burning taking place. Well, where do we find that in our body? The cell has something called the mitochondria. It is the powerhouse of each cell, the source of energy, and that's where the errors build up. So we actually even know where errors take place, where aging takes place. So what is aging? Aging is the buildup of errors, genetic errors, molecular errors, cellular errors, but we have error-correcting mechanisms. And so using gene therapy in the future, we might be able to correct the defects in cells as they accumulate errors, making them sluggish, and they eventually die. Well, the list goes on and on. The next is telomeres at the end of a chromosome. They are like a biological clock. They get shorter and shorter with each reproduction. After 60 cell reproductions, the cell begins to slow down and eventually die. In fact, some people think that's why we die. There's a biological clock. Well, you can actually reset the clock. There's something called telomerase, which allows you to reset the biological clock. But there's a danger. And the danger is cancer cells also use telomerase. Because after all, what is the main characteristic of cancer? They are immortal. That's the essence of cancer. Cells which have forgotten how to die. Cells which just keep on reproducing, pushing other cells out, creating a tumor, and killing the host. Well, anyway, I can't possibly go into all the avenues for immortality research. There's quite a bit. So I personally think that maybe not my generation, but maybe our grandkids. Maybe our grandkids may have the option of hitting the age of 30 and then stopping. They may like being 30 for many, many decades to come. Okay, well, moving right along now, let's take the next listener phone call.
Jonathan from Mineral Wells, Texas. Instead of creating a force field around something that objects bounce off of, is there any way that we could create enough radiation and try to recreate something to an extent of, say, the ozone layer? Something to the extent of maybe trying to recreate the Earth itself. I would appreciate it if that were answered.
Well, I don't quite understand, because you mentioned force fields, like repulsive force fields. Then you went in a different direction, talking about radiation, which are kind of like unrelated. However, in my book, Physics of the Impossible, I talk about force fields. You might think that some Thomas Edison someplace is going to invent a force field and change world history. all of a sudden armies and detectives, police, everyone will want a personal force field. But force fields are much more difficult than you realize. There are two kinds of force fields that we're familiar with. One force field is the force field of electricity and magnetism, and the other force field is the force field of gravity. However, of the three, none of them give you the force field seen in science fiction. You want something that is impenetrable, invisible, something like a glass shield, except is unbreakable. Well, electric fields can be neutralized by things like plastic. If I have a very strong electric field, millions of electron volts, and I can throw a piece of plastic in between, the plastic goes right through. And so there's a weakness to electricity being your force field. And also magnetism, same problem there. If you have magnetism and you throw a piece of plastic through a magnet, what happens? Nothing. And so electromagnetic force fields are not suitable for the force fields of science fiction. Gravitational force fields are only attractive, not repulsive, and they're too weak, extremely weak. Think about it. It takes 6 sextillion tons of dirt, the mass of the Earth itself, to keep you on the floor. Think about that. An object the size of the Earth, 8,000 miles in diameter, weighing 6 sextillion tons. That's what's required to keep you on the floor. So in other words, gravity is extremely weak, and we don't expect gravity to give us a force field. Radiation has the same problem. What is radiation? Broken up atoms, fragments of atoms. You have protons and neutrons and electrons, all of which give you radiation. And again, same thing there. Radiation cannot create a force field. And so the simplest thing that you see in science fiction, the force field, is actually one of the most difficult to create. Think about that. Okay, well, let's move right along to the next listener phone call.
Hi, my name's Idana. I'm calling from California, and I would like to know what's the possibility of an asteroid, instead of creating a crater, that it skimmed the Earth and actually created some of our trenches and valleys, canyons. Thanks. Bye.
Well, that's an interesting thought, but I think the probability is extremely low, very close to zero. For example, take a look at Apophis. Apophis is an asteroid about 1,000 feet across, and it's headed toward the Earth. It'll skim the Earth. It'll come right underneath our satellites. That's how close it's going to come in the year 2029 and 2036. But it's only 1,000 feet across. It's not going to create a crater. It's not going to gouge the Earth. But let's take a short commercial break. And after the break, I will try to address these questions of whether or not asteroid impacts really can create valleys and things like that on the planet Earth. Well, the short answer is probably not, for several reasons. First of all, the Earth has lots of valleys, all of which can be explained by things like tectonic activity and global warming. Tectonic activity, sorry about that. So we have so many valleys, but the probability of creating a valley with a skim by an asteroid is very close to zero. The angle would have to be so precisely calibrated that very few asteroids would be in that kill radius that would allow it to skim the planet Earth. And as I mentioned, in 2029 and in 2036, an asteroid will skim the Earth. It's called Apophis. It'll come so close to the Earth that you'll perhaps be able to see it with the naked eye. That's how close it's going to come as it soars right overhead. An object the size of the Rose Bowl, about 1,000 feet across. Potentially dangerous? Yes. Will it miss? Probably. We're not sure, but it'll probably miss. But it shows you what could happen if an asteroid comes very close to the planet Earth, capable of skimming the Earth. Will it create valleys? I don't think so. However, let's move right along to the next listener phone call.
Hi, my name is Ryan. I'm from Tucson, Arizona, and my question is regarding human cloning. Are there actual human clones walking around today? And if not, how far are we away from being able to do so?
Well, you ask a very interesting question that was in the newspaper several years ago when a cult said that they do cloning inside their cult. However, they gave no evidence. They gave no evidence that they even had knowledge of the science involved. So most people think they did that for publicity, because of course cults love publicity. So cloning means, of course, creating a carbon copy of us like a twin, but the technology is available for animals and pets. We do that now with pets. But for the most part, it has never been done on humans. First of all, it has never been done on primates. No one has ever cloned a monkey. So that would be a step in the direction of cloning humans, but we can't even do that with animals. Plus the fact that in many states and countries, there is a formal or informal ban on the science of creating a cloned human being from sperm and an egg and just DNA. And so that's why at the present time we don't have any human clones. However, if you read the New York Times just a few days ago, there was a major article concerning advances in genetic engineering, including CRISPR technology. This technology allows you to edit just like you edit an article, edit the DNA of an organism, edit the blueprint of life. Amazing. And the article went on and said that in animals, you can take skin cells and turn them into full-blown mice. This is amazing. We didn't think that was possible, but now we can do it. Taking cells from mice, hitting them with this technology, CRISPR technology, and then you create an entire mouse. This is something from nothing. Amazing. And so even though we cannot clone a human being, we can now clone mice from skin cells. Amazing technology. So anyway, to answer your question, the answer is no. We know of no instance of a human being cloned, but it's only a matter of time. Who knows? I would say within 5-10 years, I wouldn't be surprised at all if some kind of renegade laboratory claims that they have cloned a human being. Okay, and also let me say that, is it a tragedy if that happens? I don't think so. When the first test tube baby, Louise Brown, was grown out of a test tube, the Catholic Church denounced it. Ethicists all over the world denounced it. But hey, your best friend could be a byproduct of a test tube baby. You, in the audience, you could be a test tube baby. We just got used to it. So, of course, religious people can huff and puff as much as they want, but most people say to themselves, it's either unimportant for me or I want it. I want that technology because this is going to make me become a mother, make me become a father. And so there was a demand, a tremendous pent-up demand for test tube babies. Is there going to be a pent-up demand for cloned people? I don't think so. Because who's going to clone? Who's going to put up the money to clone themselves? Well, mainly rich people. So they can give their money to themselves as children and start all over again as a rich man. So personally, I think that there's not going to be much demand for cloned human beings. Okay, well, let's move right along to the next listener phone call.
Hi, my name is Adam. I'm from Birmingham, Alabama. I'm an amateur astronomer. I love looking through my 8-inch celestron. I like to focus my telescope on Beetlejuice. Statistics say that it has a possibility of blowing up soon. I was wondering if you could touch on that. What are the actual possibilities of it being during our lifetime? Thank you. I love the show.
Well, first of all, Beetlejuice is not Michael Keaton. It's not a Hollywood movie about the bizarre life after death of ghosts. Beetlejuice is a star named after a Babylonian god. And Beetlejuice is a red giant, and it's unstable. Pictures of Beetlejuice, it's very hard to, of course, photograph stars and their shape, but you can actually see a fuzzy disk that is unstable. So we do know it will explode. It is a star in its last stages, and it will explode. Is it dangerous? Not so much. You'll be able to see it at night. It'll light up the night sky, sort of like Venus, but it's not going to destroy the Earth. The star Beetlejuice, you can Google it. It's a few hundred light years from the Earth, too far to cause the damage that could wipe out life on Earth. Now, before the dinosaur theory of asteroids came out, some scientists said, including Carl Sagan, that maybe a supernova took place in our vicinity of the universe that may have wiped out the dinosaurs. Well, yes, that's a possibility. Now, of course, we lean toward the asteroid theory of dinosaur extinction. But, yeah, you can't rule it out. the fact that a supernova could destroy life on Earth, but it has to be much closer to the planet Earth on a scale of 5, 10 light years before we really, really have to worry about it. So what are the chances of it blowing up? Well, maybe it already blew up. It takes time for light to reach the planet Earth, or it could be thousands of years into the future. But just know that it's a stable, unstable red giant star, but precisely when it's going to erupt, we simply don't know. Okay, well, moving on now, let's take the next listener phone call.
Hi, my name's Sam. I'm in the state of Washington, in Spokane. And my question is it possible ever to invent a absolute cold illumination lighting system that requires no energy or output of heat of any kind? And what might be involved in such a system? Thank you very much.
Well, I just found out that I have to wind up this segment of Science Fantastic. So let's take a short commercial break. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science as we talk about science that touches our lives and can revolutionize our world. Now, before the break, we had a call. Somebody who asked a question about cold light. Is it possible to get light that gives off no heat, light that can illuminate our world and use up almost no money and no resources, and a magic light? Well, probably not, for two reasons. First, we have the laws of thermodynamics. The first law of thermodynamics says that the total amount of energy in a system does not change. You cannot destroy energy or matter. It was Einstein who gave us the latest version of that via E equals mc squared. But basically, you can't get something for nothing. So you have to input energy to create light. You have to feed electricity into a light bulb to make it glow so it gives off heat radiation. So the first law would rule out cold light that requires no input of energy. But then there's also the second law of thermodynamics, which says that in any closed system, objects tend toward disorder, chaos, tends toward falling apart. That's why we get old. That's why we die. That's why we age, because of the second law of thermodynamics. Entropy, disorder, always increases. Now, if you had a perfect light bulb, the perfect light bulb will give us no heat. But you see, that violates the second law, because every time you do work, like turning on a light bulb, you create waste heat energy. That's part of the second law of thermodynamics. And so you can't get around it. So perfect light is not possible theoretically or commercially. By the way, we should also point out that the second law of thermodynamics not only governs light bulbs, it also governs the universe. It means that the universe will eventually die. All the stars in the sky, planets, life will eventually wear out, and the universe will become very, very cold, near absolute zero. You don't have to take out an insurance policy because this is going to happen trillions of years into the future. So we don't have to worry about the ultimate death of the universe. My own point of view is that when the universe begins to die, perhaps we should leave the universe. Billions of years from now, we may have the energy and the technology and the motivation for creating a wormhole and leaving the universe in a dimensional lifeboat. Okay, well, let's move right along now to take the next listener phone call.
My name is Joe. I'm in Auburn, Alabama, and I had an inquiry about using water as fuel for cars. Thanks. Bye-bye.
Yeah, every once in a while people ask me about that idea. Wouldn't it be great that instead of putting gasoline, instead of putting fuel into your gas tank, you just put in water and it takes off? Well, I don't think that's possible. None of the friends that I have that I've asked know of a chemical reaction that gives off energy. I think what people are referring to is a high school experiment. If I get a glass of water and put two electrodes in it, one positive, one negative, connected to a battery, that bubbles will begin to form. The energy of electricity will break up the water molecule into oxygen and hydrogen. When you combine oxygen and hydrogen later in a spark, it creates an explosion and leaves water. So at first you say to yourself, aha, this must be the way to get energy from nothing. Energy from water by simply adding a spark to it and then having water turn into oxygen and hydrogen. And when you unify those two together, you get energy. Well, not so fast. It turns out that water is pretty much at the bottom of the energy scale. Mother Nature says that all processes tend to go to the lowest energy level. If I have a dam, for example, and there's a hole in the dam, water will go to the lowest level, i.e., it'll leak out. So systems always love to be in their lowest energy state. Water is one of them. That's why you're not going to be able to extract usable energy from water. Now, one day, if we have fusion plants, we'll be able to extract fusion materials from water, but mainly hydrogen-based materials. And to do that, you have to add energy from the outside. And so, can you extract fusion energy from water? Yes, because that's a nuclear reaction, not a chemical reaction. And a nuclear reaction would have enough energy, but you have to add energy to kickstart it. So, in other words, the first law of thermodynamics and the second law of thermodynamics puts a limit on what you can extract from things like fire. Okay, well, let's move right along now to the next listener phone call.
Hi, my name is Michael in Fresno, California, and my question is about hurricanes. Why there is not a resolution on how to disrupt a hurricane knowing that it's coming from an area hundreds of miles away and not have an ability to disrupt that hurricane with the knowledge that we have, possibly an oxygen disruption or any other means. Thank you.
Well, you've asked a question that a lot of people ask every time a hurricane hits Florida or hits the East Coast. People wonder, why can't we deflect it? I mean, we have so much technology. Why can't we disrupt or move out of the way the path of a hurricane? Well, we think we are masters of the universe until Mother Nature comes along and teaches us who's really boss. First of all, a full-blown hurricane has more energy than a score of hydrogen bombs. The hydrogen bomb is the most ferocious thing we can harness on the planet Earth, and a simple hurricane has more energy than many hurricanes. So you're up against a tremendous problem. So some people say, why not get a hurricane when it's still young, when it's in the cradle? We'll talk about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we explore the amazing cutting edge of science. Well, before the break, we had a question, can you disrupt a hurricane? Well, first of all, where do hurricanes come from? Hurricanes mainly come from Africa. There is a gentle breeze that accumulates in Africa. The breeze begins to move west, and as it goes westward, it picks up energy. More energy as it goes west until it hits the Gulf area. And the Gulf area, like the Gulf of Mexico, has lots of warm water. And hurricanes are like Samson. They get their energy from something. Samson got his energy from his hair. Hurricanes get their energy from warm water. And it's like a bowling ball. Take a map of the world, look at Africa, draw a line across Africa to the Caribbean, and then if you hit the angle right, like a bowling ball, you hit the angle right, you can hit New Orleans. You can hit Florida. You can hit all sorts of very valuable real estate if the angle comes in right, just like a bowling ball going across the Atlantic. Then the last question is, can we disrupt it? And the answer is it will be very difficult, because once it does reach the west coast, the east coast of North America, once it does hit that, the energy is so ferocious. The hurricane is hundreds of miles across. It's gigantic. And even a hydrogen bomb cannot disrupt it. You would have to disrupt it much earlier, in a much earlier phase. And remember that people who have tried to disrupt the weather have met with very mixed results. The CIA, for example, during the Vietnam War, was toying with the idea of influencing when the monsoon season would hit Vietnam. By doing that, they could perhaps win the Vietnam War. Their idea was to seed the clouds with things like iron iodide, silver iodide, and these ice crystals form as nuclei that allow for the condensation of raindrops. And so the theory was, by dropping particles of silver oxide over Vietnam, you might be able to create artificial precipitation and condensation and create a monsoon season when you want it. Well, it was a failure. It turns out controlling the weather turned out to be much more difficult than we originally thought. Because A, the energy of things like a hurricane is absolutely enormous, much bigger than a hydrogen bomb. And B, the weather is huge in size, and we are puny compared to the weather. Okay, moving right along, let's take the next listener phone call.
My name is Greg, and I'm from Great Falls, Montana, and I'm listening to 1450. My question is, I don't understand why we can't see an atom when a photon is the smaller particle of the molecular model. Thanks a lot. Bye-bye.
Yes, you're absolutely right. We cannot see an atom in the old-fashioned meaning of the word see, but we can see the atom's imprint. And you get beautiful pictures of atom. Just Google it on the web. These are called phase microscopes, and they're sort of like an old LP. Remember the old-fashioned LP? They had a needle. The needle would go in a groove, and it would repeat itself over and over and over again. Well, that's how we take, quote, photographs, unquote, of individual atoms. Atoms are smaller than the wavelength of light. Therefore, light is useless in terms of trying to photograph an atom. So here's how we do it. Just like an LP record. We take an object with grooves, and we take a needle, a very fine needle, just like the needle of an LP, and we move it over a surface which contains the atoms you want to photograph. The needle goes up and down as it moves horizontally, and it changes the electric field. And by measuring changes in the electric field, when you plot it on paper, what do you see? Valleys, rifts and valleys as the needle goes up and down. And then if the needle goes again and again and again to create a horizontal picture of what you're looking at, why golly, what do you see? Individual atoms. And so atoms, in some sense, can be seen. They can be seen because we can put a needle over them, and the needle bumps up against atoms as it moves across these molecules, and that's how we get, quote, pictures of individual atoms. Now, is it possible to get pictures of a proton going even smaller? That's very hard, because in principle, we might be able to create waves with a wavelength smaller than light and photograph individual subatomic particles. But the energy necessary to do that increases. So if the energy gets too high, then it rips up the atom. And so you're ripping up what did you want it to photograph. And that's why it's very difficult to use electromagnetic radiation to reveal the secrets of atoms. Well, unfortunately, our time is up.